Hello there. I'll now do section 5.2, unless most of it. I'm going to do basically almost all of it. I'm not going to do a three-way Venn diagram problem. I'm doing that in the other video. That's the last one I put on the note sheet. So I did that in a separate video, but the rest of it I'm going to do here. So first of all, just starting out with some terminology here. We're dealing with basic probability, and it's I think the majority of this is going to be Venn diagram stuff, and then also using this addition rule. But there is some terminology you need to be aware of. And look, just in general, understanding this material comes in practice, practicing problems in context, and really trying to describe this stuff. The theory may be a bit confusing, but there is some terminology you need to know. First of all, the concept of a sample space, what is that? It's just every possible outcome of a phenomenon. So if you roll a six-sided die, all right, your sample space are the numbers 1 through 6, and you could list them like this in set notation: 1, 2, 3, 4, 5, and 6, like that. So, if you're flipping a coin and the results are heads or tails, your sample space are heads and tails. So it doesn't have to be numbers, heads and tails. Or if you're dealing a card from a 52 card deck, the sample space would be every card, all 52 cards, which would be kind of tough to write out. So the sample space is just every possible thing that can happen, every outcome. The probability model assigns probabilities to every outcome. It shows every outcome with this probability. So the probability model for flipping a coin, you would say, well, my X value is either going to be heads or it's either going to be tails. And you just assign the probability to each of those. And if it's a fair coin, it'll be 1/2, like that. So if you're doing the probability model for the rolling of a six-sided die, it would just be the numbers 1 through 6. And then the probability of each would be 1/6. Okay. The key thing here is the probabilities have to be add up to 1. If they don't have to add up to 1, then it's not a probability model. So an event is just a collection of outcomes. For instance, like let's say we're dealing with this situation where our sample space is 1, 2, 3, 4, 5, and 6. We could define event A as being the outcomes of 1 or 2. Okay. Let's say we say that event B is that it's an even number. So, and these are brackets here of a set. And let's say event C is that you get a 5 or a 6, okay? So event A and C have no outcomes in common. So if I rolled a die and event A occurred, which let's pretend that event A occurred, okay, 1 or 2, you know C could not have occurred. So they exclude each other. There's no overlap. If one occurs, the other could not have occurred. Okay, and so we're going to call that mutually exclusive. Now, you notice event A and event B have an outcome in common too, so they're not mutually exclusive. Same thing with event B and event C. So mutually exclusive or disjoint means they have no outcomes in common. No outcomes in common. So if like a Venn diagram we're going to look at in a little bit, it would have no overlap. Here's event A and here's event B. There's no overlap. Okay. So the complement of event, that just means the event does not occur. So you just list, so the complement event, you list everything in the sample space that's not in that event. So A complement would be everything but 1 and 2. It'd be 2, 3, 4, and 5. C complement, and it's written like that. And this is read C complement, not C to the power of C. C complement would be everything not in C. So that'd be 1, 2, 3, and 4. B complement would be the odd numbers. Okay, so the complement of an event just means everything that is in the sample space that's not in that event. All right, so that's it for your basic terminology. I did want to write out the probability model for the sum of 2 dice, because that's something that we're going to be dealing with a lot. So when you roll 2 six-sided dice, you could get, look, I got a 12, which is hard to do. All right, so you could, that's the most you could get, and then the least you could get would be a 2. So you can get every number between 12 and 2, 3 and 4 and 5 and so forth. Okay, so list every possibility in its probability. So the probability model means list every possible outcome and its probability. So every outcome is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We're going to be doing several problems with this distribution. So that's why I'm doing this. And so the probability of each. Now let's think about this. All right. So I've written out every possibility here for when you roll 2 six-sided dice. So you could roll a 1 and a 1, a 1 and a 2, a 1 and a 3, and so forth, or a 2 and a 1, 2 and a 2, 2 and a 3. So there's 36 different possibilities for the rolls of these two dice. And by the way, a 1 and a 2 is different from a 2 and a 1. So anyway, and so there's the possible rolls. There's 36 different rolls. So to find a probability of a certain sum, you just say it's the total number of ways to have a success over the total number of possibilities. So first of all, rolling a 2. Well, there's only one way to do that. There it is. And there's 36 possibilities. So the probability of rolling a 2 is 1 out of 36. What about rolling a 3? So there's two ways of doing it. You could roll a 1 and a 2, or a 2 and a 1, and that's it. The rest of these do not add up to 3. So there's two ways of having a success over the total number of possibilities, 36. What about rolling a 4? Well, you could roll a 1 and a 3, a 2 and a 2, or a 3 and a 1. 3 ways of doing it. And so 3 out of 36 is probably that. I think you may see a pattern. The probability of rolling a 5 is going to be all these. 4 ways of doing it. It's going to keep going diagonally. So that'd be 4 out of 36, and it's going to keep going up by 1. So 6 is going to be 5 out of 36. 7 is going to be 6 out of 36, like that. So 7 is right up the diagonal here, like that of this matrix, like that. So there's 7 ways of doing it. Now you'll notice 8, it goes back, or there's 6 ways of doing that, and there's going to be 5 ways of doing that. So this would be 5 out of 36. And then there'd be 4 out of 36 to roll a 9, to roll a 10 to be 3 out of 36, and then 2 out of 36, and then 1 out of 36. So this distribution will be useful to you when you're asked problems about the sum of two dice. Just remember, it starts with 1s on the outside, and it goes up by 1 as you get to the middle. And then the bottom of the fraction, you just multiply the number of sides on one dice times the number of sides on the other dice. The last bit of theory here is what is known as the general addition rule. Is when you're asked the probability of A or B. That's what that symbol means, union, which means or. The word or in math means add. So when you're asked the probability of this or that, you add the two probabilities, but you subtract the overlap. And we'll look at examples of this. So, and that is on your formula sheet. It's one of 2 formulas on your formula. First page of your formula sheet. Probability of A or B is the probability of A plus the probability of B minus the probability of the overlap. And then that's from 5.2, and this is a formula for 5.3. So there's the big formula for 5.2, the generalized addition rule. Just remember, whenever you add probabilities, you have to subtract off any overlap. And I'll show you what I mean by that. So, okay, so let's do some examples. I think that's the best way to understand this stuff. So context 1 says this: there are 5 officers in the stats club. Sven must select 2 of them to go to the convention. Their names are Abby, Bart, Charlie, Dave, and Eleanor. If he randomly selects 2 of them, what's the probability he'll select either at least one girl, which is Abby or Eleanor? Okay. So what we'll do, and this is in the world of AP stats, we don't get into the field of math called combinatorics, which is counting, which you may have had in the past. Like this, in essence, you may know is you could say 5, choose 2 is the number of ways you could reorder these. And so, or a number of ways you could choose these, and you got like permutation. We're not doing that. All we're doing with a problem like this is just list the total possibilities and then find the probability of your successes. So list all the possibilities and then circle the successes. So list this every possibility. So you could have, let's list every one that has Abby in it. So you could have Abby and Bart. You could have Abby and Charlie. You could have Abby and Dave. You could have Abby and Eleanor. Or you could have Bart and Charlie. And you could have Bart and Dave. And you could have Bart and Eleanor. Now, and of course, note that having Abby and Bart is the same thing as having Bart and Abby. The order doesn't matter here. So then what about Charlie? You could have Charlie and Dave, Charlie and Eleanor, and lastly, you could have Dave and Eleanor. Now let's circle all the ones where there's at least one girl that have either Abby or Eleanor or both. So here, these have Abby right there. And then these have Eleanor, and then these 3 don't. So there's 7 total here when you count those up. So 7 out of the total of 10. So that's the probability of at least one girl. So that's just the technique of listing every possibility and circling your number of successes. Now, the next sort of problem deals with a probability distribution. The key thing to remember is the probabilities have to add up to 1 or 100%. So it says the probability distribution of the number of workers that show up for a shift at an office is shown below. So what this is saying is is that exactly one worker shows up 32% of the time, two workers show up 27% of the time, three workers show up 13% of the time. We don't know the percent for 4 and 5, but we do know all this has to add up to 1. So when it says, what are the values of the question mark? If the probability of 4 and 5 are the same. So this and this are the same. Well, all this has got to add up to 1. These, let's add all these up. So that would be, let's see, 59 and then 69, 72. So that's 0.72. So these two have to add up to 0.28 together, and they have to be the same thing. So they have to be 0.14. And so there you go. So that's all there's to that. Then it says, what's the probability of at least 3 workers showing up? So that would be at least 3. Well, at least 3, that'd be 3, 4, 5. So we just add those up. So that'd be 0.13 plus 0.14 plus 0.14. And that would equal to 0.41. Now, showing your work on something like this, just show the addition. Show that addition right there. And so that's it. And make sure you're cool with, some people can get a bit confused by the concept of at least 3 means 3 or more. At most 3 would be 3, 2, or 1, which is certainly different from less than 3. Less than 3 does not include 3. So it'd be that plus that. It would be 59.59. And so forth. More than 3 would be 28. It wouldn't include 3 itself. So make sure you're cool with that. All right. So now let's see here. I need a blank. I need a blank one. Okay, good. All right. So let's look at this. Here's one of the main sorts of problems. That is a two-way table problem. So really, I think all right. So there's really 3 main types of problems in this section. You've got a two-way table problem. You got problems dealing with the general addition rule here, and you got Venn diagram problems. So let's do this, a two-way table problem, which we did something like this in chapter 1. So this is asking, is there a relationship between a student's gender and what their favorite homecoming activity is? A random sample of 92 Grissom students was taken. They were asked their gender and then whether their favorite homecoming activity was the dance, the bonfire, or the field games. The results are shown below. So whenever you encounter a two-way table like this, these 2 categorical variables, you really need to come up with a marginal distribution. So that means we need to add up the columns and rows. So I'll add up the columns. There's a total, 32 plus 8 is 40, total of 40 that like to dance. That plus that would be 28. There's a total of 28 that prefer the bonfire. There's a total of 24 that prefer the field games. And you add these up, they add up to the total of 92. Then the total number of females, you go 32 plus 16 plus 5, that's 53. And the total number of males, you go 8 plus 12 plus 19, and that's 39. And so that adds up to 92 as well. So that will allow me to answer these problems. So if you were to randomly select one of these students, find the probability that, and it wants to show the proper notation, they'll say dance is their favorite activity. So that notation, I'll just use D for dance. There's none of the others that start with D. So I'll go D for dance. That means the probability of dance. Well, and so you find the total number that like dance, 40, over the total number of possibilities, 92, and that's it. Showing your work is showing that fraction. So you can just leave it like that. Okay. Now I kind of like seeing the proportion. It kind of gives me, a clear picture of what percent or what proportion are fall in that category. So anyway, but you just have, the only thing you have to show is that fraction. So, and don't simplify the fraction, just leave it just like that. All right. What's the probability they'll be male? Well, how many males do we have? Number of males is 39 over the total number of possibilities, 92. That's it. You can just leave it like that. That, as it turns out, is approximately equal to 0.4239. So you got to be able to convert it to a proportion or percent if, for a multiple choice situation. All right. So then we have, what's the probability there'll be female, and I'll put FE for female because we have a field games too. Or we symbolize that by this union symbol, or they want like the bonfire, like that. Well, there's a couple ways you could do this. You could say, well, we've got a total of 53 females. So we've got 53 females. Then we also have 12 others that like the bonfire that aren't female. So it'd be 53 plus 12. So there's a total of 65 of them. So the probability is going to be 65 out of 92. All right. But another way to do it, the most popular way to do it, and you could be asked to do this way, is to use the addition rule, which is, once again, this guy, the probability of one thing or another. You add those 2 things together and subtract the overlap. And so let's do it that way. So it's going to be equal to the probability of female plus, or means add, probability of the bonfire. And then whenever you add two things, you have to subtract off their overlap. And this would be female and bonfire. That little intersection symbol means and. And so when you do that, the probability of female, well, there's a total of 53 out of 92, plus the probability of bonfire, well, there's a total of 28 of them, 28 out of 92. And then you subtract. See, the problem is you just counted those 16 twice. So you have to subtract them off once, minus 16 out of 92. So that's sort of the logic there. And so anyway, because you counted the female bonfire people twice. And so, and that in fact is equal to 65 out of 92. So, so that's how you do that. All right. What's the probability they'll be male and say that dance is their favorite activity? So that would be the probability of male and it looks like that, and say that dance. Well, male and dance, there's 8 of them. That would be the overlap of male and dance. So that would be just 8 out of 92. That's it. Okay. All right. Then we have now these two problems are really more from section 5.3, but I'll go ahead and do them now. So what's the probability that they'll select dance given female? So the notation is this: dance given female. All right. And this vertical line segment means given. This means dance. In other words, given you know someone is a female, given the females, what's the probability they'll select dance? So what you got to do there is this. You have to look at just what you're given. We're just given the females. Given it's one of these 53 people, what's the probability they'll pick dance? That'd be 32. So it'd be 32 out of 53. So the other way of wording this, it could be worded, you know, what's the probability they'll select dance if you know they're female? Or it could say, you know, so-and-so is a female, period. What's the probability they like dance? That would be the same thing. Okay. So, all right. And so this one, what's the probability they'll be male, given that they say the field games is their favorite activity? Okay. So we're, in this case, we're just given the field games. So we're just looking at these 24 people. Those are the only ones we're given. Given it's one of those people, what's the probability they'll be male? Well, there's 19 of them. So it'd be 19 out of 24. So these conditional probabilities restrict your denominator there. And so there you go. That's how you do the two-way table problems. All right. And so then the other type of problem we have is a Venn diagram problem. So, and most of the Venn diagram problems we're going to work with proportions, but we're going to start out with this. So this says this. It says 90 12th grade students were randomly selected and asked whether or not they played a sport at the school and whether or not they have a job. So, so this table, do you play a sport? Yes or no? Do they have a job? Yes or no? So let's do our marginal distribution. So the total that play a sport, they say yes to a sport, would be that plus that, and that'd be 32. And so, and then the total that do not play a sport, that plus that'd be 58. And so that adds up to the total in the table of 90. And then the total, as far as having a job, you have a total of 8 plus 42. So you have a total of 50 that have a job. And then that plus that, you have a total of 40 that do not have a job. So our Venn diagram will look like this. So we have some overlap here. So we'll just draw it like this. And so we'll say S for playing a sport and J for having a job. And so first of all, that play a sport, we have a total of 32 that play a sport. So I'm going to write 32 at the top of the sport circle. Okay. Then having a job, we got a total of 50 that have a job. So I'll write 50 at the top of the job circle. And then this overlap region is the ones that have both play a sport and have a job. So that would be 8. So there's 8 of those. So at this point, when you're given that, you can fill out the rest of the Venn diagram. If I go 32 minus 8, well, that's 32 minus 8. That's going to be 24. And so those are the people that play a sport but do not have a job. It's these people. Okay. And you'll notice when you add up the two parts of the circle, it adds up to the whole. 24 plus 8 is 32. And similarly over here with the people that have a job, if you go 50 minus 8, that's 42. So this 42 is just this crescent shape region there. It is in essence the people that have a job that don't play a sport. And you'll notice when you add up the two parts of the circle, it adds up to that. And then lastly, what about neither? Well, these people on the outside, they do not play a sport and do not have a job. And so that would be 16. And so in a Venn diagram, these four numbers have to add up to the total. So that, but most of the time, like I said, these things will be in proportions. And so the way I can do that, so sport and job is many times we're not just interested in the number that are doing something, but in the percent of people or things that were doing something, or in the proportion. So to get that, you just divide everything by the total. So if I go 32 divided by 90, I get 0.35 repeating. So about 36% of the students play a sport. And then if I go 24 divided by 90, that is equal to 0.26 repeating. If I go 8 divided by 90, that's 0.08 repeating. If I go 50 divided by 90, that's 0.5 repeating. So about 56% of these students have a job. And then 42 divided by 90, it's 0.46 repeating. And then lastly, 16 divided by 90, that's 0.17 repeating. So that's just converting them to a proportion. So, all right. So then it says, what is the probability that a randomly selected student from the survey will play a sport or have a job? So our notation would play a sport or have a job, like that. And so we go back to our generalized addition rule. Or means add. So that's going to be the probability of sport plus the probability of job. But anytime you add two probabilities, you have to subtract any overlap, sport and job. Of course, if they were disjoint, if they looked like this, they were disjoint, there was no overlap, then this would be 0. We don't have that here. All right, so the probability they play a sport, and I'll just, I'll make the fraction. Well, you can, I'll just use this number. What the heck? So sport is 0.35 repeating, plus the probability of a job is 0.5 repeating, and then minus the probability of sport and job, which is 0.08 repeating. And then when you do these, that would be 0.82 repeating, like that. And so that's how you do the generalized addition rule. Okay. Now, and here is really the main sort of problem. So hopefully you're still paying attention, because now is the most important part. This is, well, that the Venn diagram, the two biggies are, the two-way table Venn diagram. So here's your basic Venn diagram problem. This says that 58% of people live in a village own a car, 14% own a boat, and 12% own both car and a boat. Whenever you're given the probability of one thing and the probability of another and the probability of both, almost always, most of the time, make a Venn diagram. Of course, this time it says make a Venn diagram, but I'm just saying in general. So one of the big things about probability is being able to tell what sort of problem it is, and that takes practice. And with Venn diagram problems, you recognize it's a Venn diagram, probably one thing, probably the other, probably both. So let's make our Venn diagram. So we go like this, we go like that. So 58% own a car. So we'll make our overlapping circles here. So I'll put C for car, put 0.58, right, like that. That represents the area, that whole circle. And then 14% own a boat. So I'll put B for boat. And so it'll be 0.14, like that. That represents that circle. And then 12% car and boat. So that is 0.12, that's in the middle. So that's everything we're given. It's everything we're given. So now, so what you're going to do is this. If I'm going to say 14 minus 12, that's 2, or 0.02. Okay. That is this crescent shaped region. If I take this whole circle, the 0.14, and subtract the overlap, I get 0.02. So that's the crescent shaped region, the people that own a boat but not a car. Notice the two parts to the circle add up to the whole. Similarly with the car circle, if I say 58 minus 12, well, that'd be 0.46. That represents the people that own a car but not a boat. So the two parts add up to the whole. And lastly, what about outside, the people that own neither? Realize the whole thing has to add up to 1. So these four areas, this, and the outside have to add up to 1. So you can just say 1 minus that, minus that, minus that. Well, in fact, these add up to 0.6. So this has to be 0.4. That way, the whole thing adds up to 100%. These four regions. So anyway, because everybody in the world falls in one of these categories. You either have, you own a car, you own a boat, or you own both, or you own neither. So I would be in this 46%, own a car. So anyway, So there you go. There's your Venn diagram. Now, and by the way, showing the Venn diagram is in effect showing your work for all these. So for instance, so you can pretty much have that Venn diagram and just write down your answer. But I'm going to show you also how to do the work if you didn't have a Venn diagram. So what's the probability you own a car but not a boat? Car and boat complement. Okay. Car, and you need to understand this notation here. This means car and boat complement, car and not boat, in other words. Well, you would just take all the people that own a car, 0.58, and subtract off those that own a car that also own a boat. So that'd be 0.46. So that's that. What's the probability if you select one of these people that own a boat but not a car and not car complement? So all the people that own a boat minus those boat people that own a car. So that's 0.02. That's those. All right, on a car or a boat. Well, it's going back to probability of car or boat. And that would be, you add these and subtract the overlap, just like we've done a couple times now. So the probability of car is 0.58 plus the probability of boat, which is 0.14. But whenever you add probabilities, you have to subtract off overlap. So we got to subtract off the 0.12. And so that is equal to 0.6. Okay, so the probability of neither car nor boat, probability of not car and not boat is just so the probability of neither is 1 minus the probability of either. So this is just 1 minus 0.6, and that's 0.4. Okay, it's just what's on the outside. And by the way, when it says the probability of this or that, it implies this or that or both. So that's that. Now, and so that is okay. That's the main sort of problem in this chapter. In this section, rather, right there. That's what you got to be able to handle. Now, create a two-way table. There's, I think, a problem in your book that asks you to do this. So we'll kind of go in the reverse order of what we did with the school and job example we just did. So we'll say, okay, do they own a car? And so I'll say yes or no. And do they own a boat? And I'll say yes and no. So own both a car and a boat, that's 0.12. On a car but not a boat, that's 0.46. On a boat but not a car, and that's 0.02, right? And then own neither, that's 0.12. There we go. So let me make sure I did that right. So 0.46. Now own both is 0.12. And this, no, I'm sorry, neither. I was going to say that doesn't add up. I'm sorry. So this is 0.4. Neither is 0.4. I was going to say that would disturb me because these have to add up to 1 or 100%. All right. And then lastly, for this, of course, once again, I'm not doing the three-way Venn in this video, but they wouldn't put a problem with a 52 card deck on the AP exam because not everybody knows how to play cards. And I'm not going to put it on a test, but we're going to use 52 cards to a 52 card deck to do a lot of, because you can do a lot of neat problems to illustrate concepts. So we'll have some homework and bonus problems for it. Let me quickly remind you about a 52 card deck, or teach it to you if you don't know. So in a 52 card deck, you've got half of them, you got 26 red cards, and then you got 26 black cards. All right, for the 26 red cards, half of those, 13 of those are hearts, the suit of hearts. 13, the other half are diamonds. All right, for the black cards, you got half of those, you got 13 spades, and then you've got 13 clubs. So those are our 4 suits. You got 2 that are red, 2 that are black, and then within each suit, you have 13 cards. You have that, and they are labeled the numbers 2 through 10, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then you have what is known as a jack, a queen, and a king, and an ace. We don't use jokers in what we're doing. These 3 cards, the jack, the queen, and the ace. Now, I'm sorry, the jack, the queen, and the king, they have faces on them. So we call them face cards. An ace is not a face card. I don't care what you say. It is not. We're not treating it as a face card. So those are the 3 face cards. Okay. So, and there we go. And so you've got all of these 13 cards for each of these suits. So you got a 2 of hearts, 3 of hearts, 4 of hearts, all the way through 10 of hearts, jack of hearts, queen of hearts, king of hearts, ace of hearts, and the same for diamonds and the same for spades and clubs. Okay, so this asks us, this problem here asks us, what's the probability that you'll get a heart or a face card? Heart or face card. Or means add. So I'm going to say that's the probability of heart plus the probability of face card. But whenever you add probabilities, you say to yourself, I have overlap. I counted the heart face cards twice, namely the jack of hearts, queen of hearts, king of hearts. I counted them twice for the hearts and for the face cards. So I have to subtract them off. I have to subtract off the overlap of hearts and face cards. Well, what's the probability of getting a heart? Well, there's a total of 13 hearts out of 52. How many face cards are there? Well, there's 3 for each suit and there's 4 suits. So there's 12. 3 times 4 is 12. And then how many face cards are hearts? That'd be 1, 2, 3. The jack of hearts, queen of hearts, king of hearts. So that'd be minus 3 out of 52. And when you combine those, it was 22 out of 52. Boom. That's it. That's it for really everything that could be on the test, really, for as far as section 5.2. If you have any questions about that, please let me know. Thanks for watching the video.